back again to finite difference method. In this module, we are now left with applications of finite difference method, and we would focus particularly on computer implementation of finite difference method for solution of one-dimensional heat conduction, and this should enable you to write finite difference based CFD codes for solving higher dimensional problems as well. So let's have a recap of what we did in the previous lecture. We discussed application of FDM to advection diffusion problem with an outline of different difference schemes for advection term which can take care of the oscillatory behavior, and then we discussed some general aspects of computer implementation of CFD algorithms. In particular, we discussed a choice of languages, programming paradigm, and data structures which is particularly suited to CFD programming. Now in this lecture we will take up one simple application, that is computer implementation of finite difference method for steady state heat conduction problem. So we will systematically proceed from our finite difference algorithm to pseudocode to implementation in C and C++ for a simple problem. So the stepwise procedure should enable you to use the same approach for writing your own code for more complex problems. So outline of the lecture, we will just have a relook at the statement of one-dimensional heat conduction equation, and then we would summarize or recap of the solution process and the summary of finite difference algorithms. Then we will discuss required data structures which we need for this particular problem and the pseudocode for C, C+ implementation, and if time permits we should also start off with actual program code. Now let's have a relook at a bit general statement of steady state heat conduction in a slab width L with thermal conductivity K, which is assumed to be constant, and heat generation. So this is governed by this differential equation K d to T over dx square plus Qg is equal to 0. Now this Qg could be dependent on temperature. Now boundary conditions at either end, specifically when we are writing a program, we would like to be a bit more general, and we should apply or we should provide the possibilities of different types of boundary conditions at either end. So at either end we could have Dirichlet boundary condition, that is specified temperature T is equal to T bar, where T bar would be some specified value. We could have a so called Neumann boundary condition, which essentially means the flux specification Q is equal to Q bar, where this Q is K times gradient of T, and we can have convective boundary condition Q is equal to H T minus Ta. Sorry, this Q is minus K times gradient of T from Fourier's law. Let's have a review of this FDM procedures which we discussed right in the beginning. We need to describe the domain by a grid. That would be our first step. Same thing we should translate into your computer implementation as well. And at each grid point we have to approximate our differential equation using finite difference approximation of derivatives. So this has to be translated into a code segment which gives us the appropriate matrix elements and the right hand side vector coefficients. Then once we have generated the equations at all the interior points, we need to apply our boundary conditions, come at the boundary points and apply the boundary conditions, wherein we have to modify the matrix coefficients for bounded nodes taking care of the specified boundary condition. And then once we have done that and we have got our algebraic system of equation, solve the system of equation. So basically this step by step procedure tells us a modular decomposition which should make of our code, like each step which we have outlined here could be made a separate function, a routine or module, whichever term you prefer. And now in our implementation, the example which we are taking up in the class, we would consider a uniform grid spacing extension to non-uniform grid spacings would be fairly trivial and would be left as an extension exercise to you. And we will focus on central difference scheme for discretization of our governing equation. We have got a second order derivative, so use CDS for discretization at interior points. And we would now like to provide two options in our code, the one which is based on normal finite difference method, where the vertices of the cells, finite difference cells, they are our computational nodes, or the other one which we discussed, that instead of the vertices we will consider cell centers as the finite difference grid points. So we will provide both the options in our code. And as I mentioned earlier, we want to write a code wherein we can have a different mix of boundary conditions. So we have to provide a provision for all possible types, primarily 3 types which we have discussed in our problem specification. And please remember our heat conduction equation, it should flag off an error if both BCs are of Neumann type, because in this case we might end up in a non-unique solution. And we should also provide for an option of temperature dependent source term. Now let us say that how do we proceed for designing our code. So finite difference code for solving this problem should contain one module for input of the geometry and boundary conditions. So let us call that, we are going to call this module simply as input. You can choose any other appropriate name which you might fancy. Similarly, we need another module which will generate the system matrix and the right hand side, okay, taking care of the implementation of boundary conditions. So let us call this module as system matrix. This module may itself invoke separate modules for implementation of boundary conditions for the 2 types of finite difference approximation or approaches which we had promised that we are going to implement in the code. And then we should have one module which should solve our tridiagonal system of algebraic equations. And then we should also have a separate module which will output the solution in a desired format. Now before we can design our modules, we should also decide what sort of data structures we are going to use. Now the decision of data structures would be based on what are the input and output parameters which this code is required to handle. That is, what input we should provide to solve our problems and what output do we expect from our code. And the second important consideration is that we would like to have a simple interface for different modules when it is called by the driver function, which in C or C++ is called a main function. In Fortran you might call it main program. So suppose these are our grid. Now what sort of different data structures we might have? We can define one data structure for grid related things, that is, what are the endpoints of a domain, number of grid points we would like to have, number of computational nodes we would have, and so on. So let's devise one simple data structure called grid. And similarly, for handling of system matrix, which is essentially a tridiagonal matrix, we can define a new data type called matrix. Boundary conditions, we could have different types or different mixes of boundary conditions. So let us define one data structure which we would call BC type, and we want our source term to be temperature dependent. It could be a linear function, let us say, of temperature. So we should specify, or we would provide the specification by a new data type. Let us call it as source data type. Okay. Now let us have a look at each one of these data types, at what will these data types contain in detail. So data types for finite difference code for 1D heat conduction. Okay, so what are the input data which we had? The end points of the grid, let us call it x is equal to A and x is equal to B. The number of division which we might have, so that becomes one more input. So what are our inputs? Let us list them, and then we are going to put these inputs in appropriate data types. So our inputs are conductivity. Let us use the same symbol in our code as well, we will call it K. X coordinates of both ends, like this 1D heat conduction we can think of as it we are dealing with heat conduction across a slab. One end is given by the x coordinate x is equal to A, and other end is given by x coordinate x is equal to B, or in code let us use this prefix x is equal to xb. For the right end and xa for the left end. So this we will call xa, this end we would use the symbol xb. Number of divisions or number of finite difference cells. So let us use a variable n div. Okay. So these are to be specified as geometric and metal property inputs. What else we would need in terms of geometry? Another thing which we need to specify for our grid specification is a type of finite difference approach. That is, we are dealing with usual vertex based, wherein we will have our, if there are n div number of divisions, the total number of nodes will be from 1, 2, 3 and so on, n div plus 1. So we can denote this by one parameter, let us call it FDM type. FDM type is equal to 1, and in this case number of finite different nodes, n nodes, is equal to n div plus 1. Or the second approach could be our cell centered finite difference formulation. Okay. Now this we can flag off by this parameter FDM type is equal to 0, and in this case n nodes is equal to n div. I have particularly chosen this FDM type is equal to 1 and 0 with a specific region, so that we can set in our code that n nodes is equal to n div plus FDM type. Okay. So now we are ready to formalize our grid data structure. Let us call it grid itself, starting with capital G. That's the usual convention which we follow in C or C++, that whenever we introduce a new type, the name is started with a capital letter. We can use the keyword class or struct. Let us use struct type, struct grid. Now, what are the elements of the grid? First, the two endpoint coordinates, so double XA, this is x coordinate of left end, double XB, this is x coordinate of right end. Next, we should put in number of divisions, that is definitely an integer. So, int n div, number of cells or divisions. We have assumed a uniform grid, so we will have a single parameter which denotes our grid spacing, Tx, which we will use very often. So, we can introduce a new variable of the same name, so double dx, this gives us the grid spacing. Which other input data we should put as part of this grid? The number of nodes is also related to our grid type. So, let us put the number of computational node, and let us call that as int n nodes. So, this is number of computational nodes. The finite difference approach should also be put as a part of this. Okay. So, that is again an integer parameter. So, int FDM type now this is equal to 1 for usual and is equal to 0 for cell centered approach. So, do you think we are missing anything else, any other grid related parameter which we should put as a part of this data type? So, we have already taken care of the coordinates, the number of divisions, number of nodes, dx, that is grid spacing, total number of computational nodes, and the finite difference type. So, I think that is where we should close it. So, this is an encapsulation of all information which is related to finite difference grid for this one dimensional problem. The way I put this template is fairly generic in the sense that if we had a 2D grid on a rectangle, we can easily extend this template by adding the suitable dimensions, the suitable coordinates like double ya and yb to denote the extents. Similarly, let us say int y div, which will give us number of divisions in y direction, double dy, which will give us the mesh spacing in y direction, and so on. So, this should help you writing a further program for a multi-dimensional problem. Next data structure which we should take up is that of boundary conditions type. So, let us move on to a fresh page. Now we anticipate 3 types of boundary conditions, and we should provide separate integer codes for all the 3. So the BC conditions, we have primarily 3 types: Dirichlet, and we should use an integer code for it. So suppose we use code 0 for Dirichlet boundary condition, and what data we need: specified temperature, let's call that or denote that by TB. The second one is a Neumann boundary condition, that is specified flux. Let's use an integer code 1 for it, and the specified data is basically the heat flux. Third case, the convective boundary condition. Let's use an integer code for it as 2, and what are data we need for it? We need that convective heat transfer coefficient H and ambient temperature TA. So the data structure which we define for a BC type should have all these data which we need for any of these boundary conditions. So that is, we should have one integer flag and 1, 2, 3, 4, these 4 double type variables. So struct BC, or let's make it a bit more, give it a longer name, BC type, int type, which essentially gives us the code for the BC specified double TB, which is specified temperature, double QB, which represents specified heat flux, double H, which stands for our convective heat transfer coefficient, double TA, this is ambient temperature, which is required in specification of convective boundary condition. So there is a purpose in writing these names and these comments which I have written separately. In our actual code also we will type exactly in the same fashion, so that anyone, any user who wants to have a look at our code knows that what each symbol stands for, and they can easily correlate with our problem statement. So it is always a good idea to provide ample comments whether it is in our type specification or in our modules or functions, to make our code understandable to a human programmer, and it will facilitate the maintenance, debugging and extension of our code. Okay, so we have handled the grid, we have handled boundary conditions. The next issue which we had is the handling of the discrete finite difference system, and there we can have two choices. That is to say, we have got all the matrix entries, keep all of them together. So the next thing which we want to handle is our discrete finite difference algebraic system. So it was given by A into T, where T stands for the temperature, the nodes is equal to QB, which is what? Right hand side. Now remember, this A was given for 1D problem. This A has got a tri-diagonal structure. There are only 3 diagonals in A which are non-zero, and this main diagonal we had used the symbol AP. For upper diagonal, which corresponds to the node I plus 1, we have used the symbol AE, and for the lower diagonal, in fact lower diagonal stands for, this is our matrix I, this stands for the collection of the coefficients, which we have used symbol AW. So let us use these same symbols in designing a data structure for representation of all the entries in our finite difference algebraic system. And let us call that as a matrix. So basically we need to provide a data structure which encapsulates AP, AE, AW, T and QB, all of them together. Here we can make A times the choice if you want to. We can keep AP, AE and AW, this which form this 2-dimensional matrix, as a part of one data structure. We can leave T and QB, which are simple vectors, alone. So we can decide on either choice, and other choice is equally good. So now let us opt for the second choice. We will call it system matrix only, which will be stored in this matrix, which will store the entries of our discrete algebraic system A. T and QB would be left as a standalone vectors. But if you do that, we will have to make sure that we pass these separately. So we must have an extra argument which should be supplied to our relevant modules. So struct matrix now. We do not know how many number of nodes users might specify. So we would like to provide the user with the flexibility of providing any number of grid points when a solution process starts. So we are not going to have any fixed arrays in our design. So let us use then a dynamically allocated arrays, which would be represented by pointers in this struct matrix. Double star AP, so this is our main diagonal, double star AW, this is lower diagonal corresponding to western node or I minus 1th node, and double star AE, which corresponds to the eastern neighbor. Corresponding to eastern nodes. For T and V, we will have simple one-dimensional arrays. Those also will be dynamic arrays. Okay. Next thing we have left the source term. We said source would be slightly more generic than it won't be just a constant thing. So let's introduce one more data structure for handling the source term. For source term, source was given by QG. Let's say that we use two symbols. We call it QGA plus QGB into T, that is the source is linearly dependent on temperature. So the data structure which we are going to provide, this should have these two double entries QGA and QGB. So struct source double QGA double QGB. Okay, those of you who might be looking at this code pieces for the first time and may not be very well conversant with C or C++, this double basically represents a double precision, or what we call double precision real number, and int stands for integers. Okay, so now we have got most of the data structures designed which we need for our code implementation. Now we should go for the pseudo codes for modules. Now whenever we want to write a program, the very first step is to write a pseudo code. Pseudo code may be what we call a simple description in everyday English language, which can be easily translated into our computer code lines. That's what we mean by pseudo code. Okay, and this should be done before we can before we go to type in our code in a development environment or in an editor. So we should first decide what different algorithms we are going to use for, write down those algorithms, decide on the data structures, and then write pseudo codes for each module, then translate that pseudo code for that module in a code, test it, and then combine all the modules together to get our final code. Okay, so now these are our modules which we have decided we are going to put in. The first module we called it input, which will read the information or input data for grid, boundary conditions and sources, and the second one which we said was our system matrix, to which we would provide our grid data, BC type, matrix and right hand side vector. And the third module was which we had was solve, to which we provide our matrix, right hand side vector and then the solution vector. So it will return the solution in our solve vector. And the fourth module was your output module. We provide sol as input parameter and it should print our solution in a specified format. So now let's have a look at the pseudo code for each of these modules before we proceed for actual typing this code in a development environment or into an editor. So, first we will take up the case of this pseudo code for 1D FDM program. So, first we will take up the case of the pseudo code for input module. Okay, so what is input module supposed to do? It is supposed to ask the user to input all the required data. So, first thing, and our code should prompt the user to input certain set of data. So, this is what we will write here: read XA, YA and number of divisions. This would be the first input which this module should ask from the reader, and based on this input it should compute mesh spacing, dx, then it should read, it should ask the user or prompt the user to input that finite difference type. So, read FDM type, and once we have got this FDM type, next thing is compute number of computational node, and nodes. Okay. What else we need in input module? So, this is the input and the corresponding computations which give us basically basic geometry. Next, we have to ask the user input boundary conditions. Boundary conditions at each end, and what sort of data we expect? We expect the user to input the code, TB, QB, H and TA. The data which is not required for a given boundary condition should be just in that place. The user should simply input 0. So, we should prompt that information. Suppose we have our code is 0, we need only TB data. Remainder QB, H and TA, for that the user should simply input 0. Or if you want, we can also build that information in our code that which ones to read. So, we can prompt the user to only input TB or QB or H and TA. So, that decision we can make as a simple refinement to a code which we can incorporate while coding our input module. The next set of input which we need is that related to the source term. So, input source term data. Okay. So, that completes our pseudocode for input module. Now, each one of the tasks which we listed, that was that is what we mean by pseudocode, that write in plain English what each statement or a set of statements are supposed to do. So, read X, A, Y, and A, this can be translated into a single line of the code. Similarly, this compute spacing of dx, this again gets translated into a single line of code, read FDM type, a single line of code, and so on. Whereas these ones, input boundary condition at each node, this might lead to a block of the code. There might be few lines of code here. The same holds good for input source term data. But nevertheless, when we hold these refinements, okay, if there is something which requires many more set of actions to be performed, that can be refined further, that can be extended further before we translate that into a code. So, our pseudocode in that case would look a bit longer, which we will see in our next module. Okay, so next module is our system matrix. Pseudocode for module system matrix. Okay, what are the main tasks which we need to do here? We have got all the geometric informations, the source term information, and that information has to be supplied in this parameter list for this to this module's system matrix. First task would be compute elements API, AWI, AEI and QBI for each internal node. So, that way we have basically formed the disk a particular line of or a particular row of our algebraic system. Next, incorporate the boundary conditions. Boundary conditions at each node. Now, here this single statement has to be refined further, because we have got we may have different set of boundary conditions and a different modification would occur in each case. So, the details has to be further expanded. So, that we will take each of these nodes and we will have 3 distinct set of modifications. One set at if our BC type is equal to 0, you have got one set of actions or modifications. These we are going to elaborate later in more detail, so that we can translate each of these into actual code lines. My BC dot type is equal to 1, another set of actions, and third, if BC type is equal to, so third set of actions. Now, please remember that incorporation of these boundary conditions would also depend on a finite difference approach which we had chosen. So, what we should do is transfer these incorporations in 2 different submodules with correspond to two different finite difference methodologies type. So basically we are going to put these modifications in separate module if FDM type is equal to 0, which stands for self-centered formulation, call BC mod modification centered. So this is a new module. We will look at its detailed pseudocode in the next lecture. Else, that is our FDM type is equal to 1. So we will have BC modification simple. Okay. So we will have a detailed look at the pseudocode for these two sub modules later on. Okay, for the time being, let us complete the sequence. The next one which we had was our solve. Pseudocode for solve module. We would basically call an external function. We have not yet learnt the solution of algebraic equations. So we will assume that we have already got from somewhere a algorithm based on, or a subroutine based on tri-diagonal matrix algorithm. So this solve will simply have one line in a pseudocode call TDMA function to solve our system. And D, we have got our output module. The pseudocode for it is again very simple, one line. Output the temperature in tabular form. Specifically, we would like our program to output node wise information. There is node number, x coordinate and temperature. So we would like to have this tabular form. Okay. So in this lecture we would stop at this point. In the next lecture we will have a detailed enumeration of the submodules of system matrix, the pseudocode for that, and we will have a look at a full code, translated version of these pseudocodes in actual C or C++ code, and we will try and solve two example problems live in the class.